So I was working on plasma thrusters for small satellites called CubeSats, the size of a loaf of bread maybe, or the size of a shoebox. And I came to the conclusion that this is a very difficult problem because we have restrictions in terms of the amount of gas we can put in the tank, but also complicated electronics and requirement for high power. So I decided to investigate alternative propellants for small satellites. So we looked into naphthalene. Naphthalene is the main chemical in mothballs, so it's readily available, it's cheap, it's non-corrosive, unlike other propellants that can be corrosive and therefore require special treatment in the materials that they, or the surfaces that they come in contact with. So we obtained a small amount of naphthalene and did some tests in Wombat, the space simulation chamber, and we came to the conclusion that this could work for a simple thruster system.
With the naphthalene thruster, you have a box, you heat it up, and you have a valve, and you let the naphthalene out. It is really simple. Whereas mostly thrusters have quite complicated electronics. You have, to produce ion beams, you need to produce a plasma, you need to accelerate the ion beam, then you need to neutralize the ion beam with an electron source. You have a large number of areas where something can go wrong. If you try and use gases for propulsion such as xenon or krypton, you have to have a pressure vessel, and rocket companies don't like you having a pressure vessel with 200 or 500 atmospheres in it because it's possibly quite dangerous for the payload. The advantage with the naphthalene is it gives quite a respectable amount of thrust, comparable to what you would get with some of the small ion thrusters, but it's not very efficient. It uses a lot of fuel to do this. But since we don't have all the rest of the electronics and the electron neutralizers and the gas containers, we have a lot more mass that we can play with, so we can use a lot more propellant.
The oldest reference I could find was from 1963. However, in 1963 the average satellite was something like $100 million or more, and they wouldn't necessarily compromise with a slightly lower performance that you get from a cold gas thruster using naphthalene. It becomes suddenly relevant because in the CubeSats, the small satellites that do not have the power reserve that the larger satellites have, and they do not have the budget as well of big satellites, it suddenly gives an option that is quite viable. It's a very simple system, consists of a reservoir and a valve, so nothing particularly complicated. You don't have complicated electronics associated with it, and the requirement for power is very, very low. So suddenly it gives an option to CubeSats to have a propulsion system that they wouldn't otherwise have. Having a propulsion system on a satellite is a very good idea for a number of reasons. It will allow you to stay longer in orbit, and if you have made an investment on a satellite, obviously you would like to get the best value out of it if you can.
These small thrusters can be used to position satellites.
It may allow you to modify your orbit to avoid a collision with some space debris.
If you can maneuver these around, you can control constellations. These can be useful for a whole variety of reasons, for astronomy, for communicating with aircraft.
The third option that it offers you is that you can decommission your satellite a lot quicker. Rather than wait for it to naturally decay, you can use your thruster to bring it down a lot quicker, which is the responsible thing to do.
Dimitri was doing this in his PhD, and we thought, well, we can possibly put this into orbit because a company called Skycraft, who's also in Canberra, had a system called Skyride, and my company, Boswell Technologies, said what we'll do is grab one of these possible Skyrides. Boswell Technologies can pay for it, and the lab here at the ANU can build the thruster, all of the components, the mechanical and electrical components, and with luck we should be able to do it in 6 months and have it in space by mid-2022. One of the important things that I really like about it is that although I'm a physicist, I'm also CEO of a company, and the company can work with the ANU, with the group Space Plasma Power and Propulsion, to push their inventions out into the commercial sphere. So this allowed us to go through Boswell Technologies to Skycraft to get into space, and we think this is a really, really good model for universities interacting with the outside world. After all, the outside world provides money for universities to work. Universities should do some of their work to help outside companies to operate.
Initially, when I started working on this, I thought it's an academic exercise, something to help me graduate and maybe write a paper, and that's all great. And we did that. And the fact that it's going to be launched in space in the coming 6 months is quite exciting, because I see something that was a proof of concept becoming an actual product that will be installed on a real satellite, and it will change its orbit. So that's really exciting.